The next example, referring to the circuit shown, find alpha, omega naught, I of 0 plus, and di dt of 0 plus, and then find the value of I at t equals to 12 milliseconds. So first, let's analyze the circuit at t less than 0. So assuming at t less than 0, the circuit is running at steady state, or is running for a very long time. So from negative infinity to 0. So we have equivalent circuit of, so our inductor is shorted, and we have an open circuit for the capacitor. Then since our source is multiplied with a unit step u of negative t, so at t less than 0, the argument is positive. So this means that our current source is on. We have 1 ampere. This is 100. This is our V, then our I. So we can say that our I at 0 minus just equal to 1 ampere. Then our voltage at 0 minus just equivalent to 1 times 100. So we have 100 volts. So take note that the current I does not change abruptly. So the I of 0 plus minus is just equivalent to I of 0 plus. So the same with the voltage, since the voltage V is across the capacitor, so the voltage at 0 minus just equal to V at 0 plus. So immediately we have our answer for our C, question C. Next, we analyze a circuit at t greater than 0. So at t greater than 0, we have inductor, an RLC circuit. For t micro. So we have a source-free RLC series circuit. Now for A, find the value of alpha. Alpha is just equivalent to R over 2L equal to 100. Next is find for the omega. Omega naught. Omega naught is just equal to 1 over square root of LC, which is approximately equal to 224 rad per second. So this is rad per second. Next, let's find di of di dt at 0 plus. So similar with the previous example, we can express the voltage across the inductor as LDI over dt. We have di of dt at 0 plus equal to VL of 0 plus over L. Applying KVL and Ohm's law, for VL is just equivalent to V of 0 plus minus I of 0 plus times the resistance over L. So we have 100 minus 100 equal to 0. Now for E, first we need to find the expression of I of t. Now, since our alpha is less than omega naught, so our circuit is underdamped. So the underdamped expression for I of t equal to e to the negative alpha. We have negative 100t times v1 cosine of wd t plus v2 sine of wd t amperes at t greater than 0. So our omega t is equal to square root of omega naught squared minus alpha squared, is approximately equal to 200.44. So at t equals to 0, we can solve for the value of b1. So we have I of 0 plus 1 ampere. 1 goes to b1 plus, so sine of 0 is 0. So we have our b1 is equal to 0. Next, we need to differentiate this equation. We have d I dt equal to negative 100 e to the negative 100t b1 cosine of 200.44 t plus b2 sine of 200.44 t plus e to the negative 100t times negative 200.44 b1 sine of 100.44 t plus 200.44 b2 cosine of 200.44 t. So at t equals to 0, we have 0 equal to negative 100 times 1 plus 0 plus 200.44 b2. Solving for the value of b2 is equal to 0.499, or approximately equal to 0.5. So the expression for I of t equivalent to e to the negative 100t cosine of 200.44t plus 0.5 sine of 200.44t amperes t greater than 0. So the I of 12 milliseconds 12 milliseconds, so we have approximately equal to negative 0.1220 ampere.